Hi, my name is Angel, and I'm working with Sarah and Alexander. In this video, we're talking about chemical bonds, ionic compounds, type of bonds, and electron negativity. Chemical bonds hold a pair of atoms together by the positive and negative nucleus. It can be illustrated by the electron bond structure. In this model, we also see the valence electrons. This shows how much reactivity between the atoms. Cations are positive charged ions, usually are metals. Metal ions are more reactive and they easily lose electrons. Transition metals are hardly predictable in how much electrons they lose. This is because they will lose s electrons and d electrons. The number of electrons lost depends on the quantity of the electrons. Not all configurations are perfectly stable. Isotopic gas configuration is one of them. It forms on group 11 to 14 that make an outer energy level of s, p, and d sublevel. Like zinc, zinc in this configuration will lose 4s electrons. Nonmetals easily gain electrons and always look for a stable octet. In order to gain an electron, it needs a negative charge ion that is called an anion. Anions use a suffix that is "-ide", like chlorine changes to chloride. Now we pass to ionic bonds and ionic compounds. Ionic bonds are the force that make opposite charges attract. Compounds with this force are ionic compounds. A type of ionic compound is binary compound because it has two different elements, metals, cations, and non-metal anions. Ionic compounds have a unique physical structure. The cations and anions coexist by a ratio of metals atoms and non-metal atoms transferred. Make this attraction of the opposite charges. It is a 3D arrangement that positive ions are around negative ions and vice versa. Ionic bonds are not electrically conductive since they are driven by the bonds, but in liquid form they can conduct particles freely. These are called electrons. Ionic compounds only react in releasing energy. They only always connect substrate reactions. If they absorb energy, the bond will collapse. The strength of the bond depends on the lattice energy. Lattice energy is required to separate one mole from the ions in the ionic compound. Now let's talk about ionic formulas. The ionic compounds are written in a chemical unit that is called a formula unit. The ionic compounds are composed of two monoatomic ions. These monoatomic ions equals to the oxidation state. Remember, ionic compounds have zero charge, which means that by adding the oxidation number and then multiply it by the quantity of ions, it should be equal to 0, shown in the example below. A polyatomic ion is an ion that is made of multiple atoms. For example, oxyanion that is made of an element that is usually a nonmetal bonded to one or more oxygen atoms. Now we pass on writing ionic formulas. Writing an ionic formula is very simple. First, the cations go on the left and the anions go on the right. Write the number of the ions in the compound, which are the subscripts. If it has only one ion, then don't write a subscript. Polyatomic ions act as individual ions, so it applies the same rule. But if an ion is needed, just write a parenthesis around the ion and place the needed ions outside, as you can see below. Now, naming ionic compounds. First, identify the cations and the anions. Then, write the cations first, then the anions. The cation's name stays the same, but the anion's name is left with the root name and then has the suffix of "-ion". The oxidation number is located between your parentheses after the cation in Roman numerals. This rule is applied when the oxidation number is squared. name it in place of the anion or the cation. Now we're gonna talk about metals. Metals share the same properties with ionic bonds, but they aren't ionic. They both are bonded between unlike charges and form lattice energy as crystal lattices. Metals are not ionic because they don't share electrons. Instead, the outer energy levels overlap in each other. In the electron C model, electrons don't bond. Instead, they just move around. These freely moved electrons are named delocalized electrons. In this outer energy level, metal cations are formed and bond with electrons. This is how metallic bonds work. The metallic bonds explain all the physical properties of metal. Metals have a boiling point so high because of the freely moved electron. Their boiling point is so high because it is difficult to separate the cations with the electrons, since they are freely moved. The malleability of metals is allowed because of the particles of metals are easily to be pushed and pulled past each other. Metals are good conductors because of the delocalized electrons. They move the heat and the electricity from one place to another. And the strengths come with the number of electrons. Transition metals have more strength because they have s electrons and d electrons.
Some alloys vary in properties depending on how they are manufactured. In the case of some metals, different properties can be solved based on heating and cooling. In Table 13, the table lists some of the properties of alloys with their common name. Composition. An alloy of titanium have been union. This is with the bicycle frame. Show it picture. Alloys such as this are classified into one of the two basic types: substitutional alloys and interstitial alloys. This is all from metal alloys. Let's discuss covalent bonding. Covalent bonding generally can occur between elements that are near each other on the periodic table. The majority of covalent bonds form between atoms of nonmetallic elements. Example in negative side, but they're attracted when it's positive and negative. Example in figure 3. Two paired atoms share a pair of electrons to form a covalent bond. Note that the shared electron pair gives each other a complete opposite. Take as an example figure 4. The single covalent bond is a hydrogen molecule, also known as H subscript 2, a covalently bonded atom, equally attracting pair of shared electrons. Note that the two shared electrons belong to each other simultaneously, giving each hydrogen atom the noble gas configuration. Figure 4, shown previously, is written in Lewis dot structure. The line is used to symbolize a single covalent bond. The line has the value of 2 valence electrons. Example, an ammonia particle, NH subscript 3, has 3 single covalent bonds. 3 nitrogen electrons bonded with the 3 hydrogen atoms, leaving 1 pair of unshared electrons on the nitrogen atom. Example, a methyl molecule CH subscript 4 bonds with 1 carbon atom, bonds with 4 hydrogen atoms. Carbon has 4 valence electrons. Carbon still needs 4 more electrons for a noble gas configuration. When carbon bonds with other atoms, it forms 4 bonds. Because a hydrogen atom, a group 1 element, has 1 valence electron, it takes 4 hydrogen atoms to provide the 4 electrons needed by a carbon atom. Examples: carbon, nitrogen, oxygen, and sulfur atoms often form multiple bonds with other nonmetals. Example: atoms of the element oxygen only exist as diatomic molecules. Each oxygen atom has 6 valence electrons and must obtain 2 additional electrons for a noble gas configuration. Example: the atomic nitrogen molecules N subscript 2 contain a triple covalent bond. Each nitrogen atom shares 3 electron pairs, forming a triple bond with the other nitrogen atom. Of a sigma bond and a p bond. An endothermic reaction is one where a greater amount of energy is required to break a bond. Then, reactants are released when the new bonds form in the products. An exothermic reaction is one where more energy is released than is required to break the bonds in the initial reactants. To be able to name the atom compound is by following the rules. Binary molecular compound naming rules. The first element is always named first using the entire element name. The second element is named using its root and added suffix "I". Prefixes are used to indicate the number of atoms of each element that are present in the compound. Let's do N subscript 2. Oh, as an example with the rules. N is the element symbol for nitrogen. O is the element symbol for oxygen, so the second word will be oxide. There are 2 atoms of nitrogen and 1 atom of oxygen, so the first word is the nitrogen and the second word is monoxide, forming the nitrogen monoxide. Just like the binary molecular compound have a set of rules to follow, to have in the naming process, the binary acids have their set of rules too. Binary naming rules. The first word has the prefix hydro to name the hydrogen part of the compound. The rest of the first word consists of the form of the root of the second element, plus the suffix "ic". The second word is always acid. Example: HCl. Hydrogen and chlorine becomes hydrochloric. HCl in a water solution is called hydrochloric acid. Oxyacids naming rules. First, identify the oxyanion present. The first word of an oxyacid name consists of the root of the oxyanion and the prefix "er" or "hyper". If it is part of the oxyanion's name, the first word of the oxyacid's name also has the suffix that depends on the oxyanion suffix. If the oxyanion may end with the suffix "ate", replace it with the suffix "ic". If the name of the oxyanion ends with the suffix "ite", replace it with the suffix "ose". The second word of the name is always acid. Let's take as an example HNO subscript 3. NO subscript 3. The nitric ion becomes nitric. HNO subscript 3, which is hydrogen, and the nitric ion it becomes nitric acid. The name of a molecular compound reveals the composition if it's a binary molecule compound or an acid, binary acid or an oxyacid.
Thank you, Sarah. Well, I'm Alex. Today, I'm going to be presenting to you the structural formula is one of the most useful molecular models. It uses letters, symbols, and bonds to show relative positions of atoms. You can predict the structural formula for many molecules by drawing the Lewis structure. This is figure 13. In this figure are found many letters, symbols, and types of shapes that the molecules will take place in. To draw a Lewis structure, a certain procedure must be followed. The atom that has the least attraction for shared electrons will be the central atom of the molecule. You know that hydrogen is always a terminal, or the end atom, because it can share only one pair of atoms. These are the methods for creating order. In step 2, we determine the number of electrons that are available for the bonding. Step 3 was determine the number of bonding pairs. And in step 4, we must place the bonding pairs together. In step 5, we determine what the electron pairs are made in. In this problem, we have ammonia as the example. To find the total number of valence electrons, we have the 1 nitrogen atom times 5 over 1 plus 3 hydrogen times 1 over 1. This equals 8 valence electrons, and because they are in pairs, we divide this by 2, equaling 4 pairs. Then we place a bonding pair between the central nitrogen atom and each terminal hydrogen atom. This leads to only one pair available. We subtract the number of pairs used in these bonds from the total number of pairs of electrons available. This last step is very easy. We simply add the last remaining lone pair to either the terminal atoms or the central atom. This is because hydrogen atoms can only have one bond since they have no lone pairs. Then we evaluate the answer. Stay the same. The actual nitrate ion is like an average of 3 resonance structures. The dotted lines indicate possible locations of the double bond. This is an example of a suboctet. It's an exception to the octet rule. It forms stable configurations with fewer than 8 electrons present around an atom. These are bond angles. Electron pairs in a molecule are located as far apart as they can be, just as these balloons are arranged. 2 pairs form a linear shape, 3 pairs form a triagonal planar shape, and 4 pairs form a tetrahedral shape. Now, listen closely. The shapes of food molecules are determined by their chemical structures. When a molecule enters a taste bud, it must have the correct shape for the nerve in each receptor cell to respond and send a message to the brain. The brain then interprets the message as a certain taste. When such molecules bind to sweet receptors, they are sensed as sweet. A hybrid occurs when 2 things are combined and the result has a characteristic of both. For example, a hybrid automobile uses both gas and electricity as energy sources. During chemical bonding, different atomic orbitals undergo hybridization. In this figure, a carbon atom's 2s and 2p electrons occupy the pair takes up a greater amount of space than the shared pairs. There's a stronger repulsion between the lone pairs and the bonding pairs than between two bonding pairs, and the resulting geometry is a triagonal pyramidal with 107.3 bond angles. However, water has two covalent bonds and two lone pairs. Repulsion between the lone pairs causes the angle to be 104.5. As a result, water molecules have a bent shape. In this example, we'll use phosphorus trihydride. We must first analyze a problem, and we know that this molecule has three hydrogen atoms bonded to a central phosphorus atom. Then we must start to solve for the unknown, finding the total number of valence electrons. Here we start with a mathematical procedure. We have one phosphorus atom times 5 valence electrons over one phosphorus atom. We add 3 hydrogen atoms times 1 valence electron over 1 fluorine atom, which gives us 8 valence electrons. Of course, these come in pairs, so we divide this by 2. Then we draw the Lewis structure, and we use one pair of electrons to bond each hydrogen atom to the central phosphorus atom. According to the difference in electronegativity, we must determine the bond character. As you can see, this table shows the different bond characters and the covalent or ionic pairs. This graph shows that the difference in electronegativity between bonding atoms determines the percent ionic character of the bond. Above 50% ionic character, bonds are mostly found ionic. As an example, you can try to determine the percent ionic character of calcium oxide. This figure shows how often network solids are cut in cutting tools because of their extreme hardness. Here, a diamond saw blade cuts simply through stone.